Thanks everybody for coming. It's my pleasure to introduce Dr. Mercedes Pozo Buil, or Mer. Mer got her 2 bachelor's degrees at the University of Cadiz in Spain, and then her doctoral degree at Georgia Tech University. And she's a physical oceanographer interested in climate modeling, climate change, ocean and climate dynamics, and decadal variability, as well as its impact on marine ecosystems. And right now she holds an appointment at UC Santa Cruz and the Ecosystem Science Division of the NOAA Southwest Fisheries Science Center in Monterey. So thank you for coming to visit us, and we'll let you get started once we log in.
This can happen again? Okay. Well, thank you so much, and thank you for inviting me to come here. So yeah, my name is Mer Pozo Buil. Today I'm going to talk about shaping the future of the California current system, insight from seasonal forecast, and also climate projection. So this talk is going to be a little bit about all of the tools that I have been working for the past many years. The motivation of this work comes because when we have a skillful forecast of the ecosystem, we can provide the decision makers with the information that they needed to make effective long-term ecosystem management strategies. So if we think about what are the space and also the time scale of this decision, in here we are showing in the bubbles, they are just the decision for the fisheries. And then when we have the cloud, is the climate processes that are related also to them. So we can say that a start point will be, if we wanted to have good fisheries prediction, a start point will be having good, skillful physical climate forecast, and then we can connect those to a statistical and also mechanistic model of the ecosystem that we are interested in. So I'm going to be talking about 3 time scale, everything focused in the California current system. I will be talking first about the seasonal to interannual forecast, then decadal prediction and long-term climate change projection. But the outline of the talk is a little bit different. I'm going to start from the seasonal to interannual forecast, and I'm going to be showing a forecast downscaling system. Then I will move to the climate projection, and then I will show the decadal prediction that are more based on the mechanistic ocean circulation. So the goal of these 2 time scale of these 2 tools that are the seasonal forecast and also the climate change projection is to build a downscaling framework where we can produce high resolution seasonal forecast and also climate projection of the ecosystem variables in the California current system. And for those that are not familiar to what is a downscaling system, what we do is we start from the global climate model where we have the couple dynamics and also the radiative forcing, and the output of this global model serves as an input of regional model where we have better resolution and we can resolve fine scale processes. And then the output of this regional model can serve as an input of ecosystem model where we can exploit the physical and the biological relationship. So starting from the seasonal forecast downscaling system, so we start from a global climate forecast. In this case, it's the Canadian coupled climate model version 4 that has 100 kilometer resolution. And this model is part of the North American multi-model ensemble that is basically a lot of forecast system. And we pick this particular one because it has been shown in the literature that has some forecast skill to make seasonal forecasts in the California current system. So what we do, we take the output of this global climate forecast and we use it to produce the input of a regional ocean forecast. In this case, this is just a regional ocean model. It's called ROMS with 10 kilometer resolution. And our forecast configuration is, again, 10 kilometer. We pass from 100 kilometer to 10 kilometer. And we are going to be building a retrospective forecast. And they are called like that because they are going to be forecasts of the past. And it goes from 92 to 2010. The other component is we are going to be doing 12-month forecast or reforecast. We are going to be doing it only we are going to initialize this forecast twice per year, in January and July. And the reason why is because dynamical downscaling is really heavy from the computational point of view. So we pick these two months of initialization. And then we are going to be downscaling 3 ensemble members that come from the Canadian model. And the 3 ensemble members that we pick, they are, one of them has a good forecast skill, another has a really bad forecast skill, another one is in the middle. And we pick these 3 because with those 3, it's like you're representing the typical case where you have 3 members and one is bad and the other is better, basically. So we did 2 kind of experiments with this forecast. One of them is we take the output of the climate forecast and we directly interpolate it on the grid of the forcing of a regional model, and then we run the model. And this is what we call direct interpolation case. And then we did another one where we bias corrected the output from the global model, because not all of the global model are perfect, so they have some biases. So we did some bias correction of the forcing of the global climate model, and we did that we compute first the anomalies that come from the forecast, and then we add those low resolution to high resolution climatologies that we have for a forcing that we consider is the control run from our model simulation. And we apply this to everything, to the atmospheric forcing, the ocean boundary condition, and also the initial condition. So this is an sample of how this forecast or seasonal forecast look like. This is just sea surface temperature. And I'm focusing here on a region that goes from 75 kilometers to the coast. So this is just averaging all of the region in the California current system. So in black, I'm showing just the observation that we wanted to be forecasted. And then we have the 2 experiments of the forecast. The one that has been bias corrected, the one that are direct interpolation, and then the other one are the one that we have applied the bias corrected before doing the downscaling of the forcing. So in green, there is the one that is bias corrected. We can see that it's more similar to the observation that we have. Another part that I haven't mentioned here is if you see the bold line is the ensemble mean of the forecast, and then the shading is related with the 3 ensemble members that I mentioned that we were doing. So yeah, and then this dot represent when we initialize all of the forecasts. So if you see, once we apply a bias correcting forcing for the forecast, we get a better solution of the sea surface temperature that we wanted to reforecast. I'm sorry that I'm repeating that word so many times. Another way of looking at this, instead of showing you the time series where you're not going to really look many things, is with this anomaly correlation coefficient that is just it's a way of measure the forecast skill. And it's basically a linear relationship between the forecast and also the observed variable that we are taking. In this case, it's sea surface temperature. But the thing that you wanted to remember here is when we have an anomaly correlation that is 1, is when we have like a perfect forecast. And then we also have some significant skill and another line that we consider that the forecast will have no skill. So we can see that if we try to forecast in the lead time with the month in here in the x-axis, we see that we get some forecast skill up to 6 months. So once we pass 6 months, all of our forecast skill is poor. We can look at other variables. We have bottom temperature, sea surface high buoyancy or stratification, and we see that more or less, except the stratification, we get a good forecast skill up to 6 months. So this is pretty good. But we also have bad variables that we cannot forecast. And some of them are related with circulation. We have mixed layer depth, the current, the U and B component, also the wind stress, and the wind stress curve. So for all of these variables, we see that we can only get forecast skill that is significant up to 1 to 2 to 3 months if you wanted to squish it really much. Another way of showing this kind of forecast skill is, instead of showing you this kind of time series, is with a matrix that look like this. That is how usually people show the forecast skills or seasonal forecast. So here you just notice that the x-axis is the same. It's the lead time of the month that we wanted that we can get forecast skill. And then in the y-axis, we are showing just the different variables that we have. And again, now the color bar the color shading will represent the value of the anomaly correlation coefficient. So we can see that how sea surface temperature is high, sea surface high is higher, or we got a forecast skill of more than 0.8 or next to 1. But we have the other variables that I was mentioning before, that they are good, and the ones that are poor, that we have poor forecast skill. But one thing that I wanted to grab your attention, and this is bringing it back to the why the bias correction of the forcing or not, is like if we take the same matrix, and this is just considering the bias correction one, we can see what is the influence in the bias correcting forcing. If we, I'm sorry, I don't know how to remove this. I'm going to try my best. I hope I don't do anything bad. See, now I did something bad. I'm sorry, but I just wanted you to see the full equation. How can we fix this? Like full screen, probably. Or not. Oh, and now the thing doesn't appear, so great. So think that this matrix is, if you consider this one minus the one, but done with the one that we haven't done the bias correction of the forcing. So we can see that when we, so this is just the bias in the anomaly correlation coefficient. So we can see that when we bias correct in the forcing, we get more forecast skill for variables like bottom temperature, also all of the surface current, and also the mixed layer depth. That is the one that I was pointing before. And also this is surface height. So I just showed you that we can get good forecast skill for some variables, but we also have seen some variables that we don't get a good forecast skill. And also we get better forecast skill when we bias correct in the forcing prior to downscaling. Now I'm going to show you an application of this seasonal forecast. So in this case, we are going to change a little bit what I showed you. So we are going to start from our global climate forecast with downscaling to our regional ocean model, but we only take the one that has been bias corrected. So just forget about the direct interpolation one. And we are going to apply it to some ecosystem variable. But we are going to be comparing, it's going to be the same 3 ensemble member, but there is going to be a difference in this case. In this case, because we only have forecasts that are initialized twice per year, we are going to be comparing with the forecast that has been initialized every month. Because when we have global climate forecasts that are this core resolution, they are cheap to run, so you can make everything that you wanted versus these dynamical downscaling forecasts that take a lot of time to run and also a lot of the computer power. So we are going to be, I'm going to be showing you how these two forecasts compare when we compute this habitat compression index. And this index just tracks the amount of the area where the sea surface temperature is less or equal to 12 Celsius. And just, I don't know if you're familiar with this index, but it's basically telling you how much of the boiling habitat you have in the ocean. So think about it that when you have a low habitat compression index, it means that you have high habitat compressed because you get less area of your region in here where you have less boiling waters or water that are less than 12 degrees. So this is going to be bad because once you have less area with cold water, you are going to increase the probability of the entanglement risk because you are going to have more fishing gears or more fishing or more human activities happening in a small area. So this index is really important for that because it can tell you an idea of how it's going to be the probability of the entanglement risk that I cannot pronounce a word. So again, these matrices, now just notice that I'm not showing the anomaly correlation coefficient and change it to something called forecast accuracy. And this matrix is really just it's just a ratio of how many of your forecasts are true. So it's going to take all of the negatives that are true or all of the positives that are true, and then you divide it by the total forecast that you do. So if you get a number of forecast accuracy that is near 1, it means that you have done your forecast perfectly. So we are comparing here, now in the y-axis we have the lead time, and in the x-axis we have now the forecast month. So again, with the regional ocean model, with the dynamical downscaling system, we can only do two of the forecasts. So one are the initializing in January and the other one that are in July. And then we have, if we compare it with the global model, you get an initialization every month. But it's really hard to compare the two like this. So I wanted to show the difference between the two. So if we compare the forecast accuracy of this one minus this one, now everything that is blue, it means that the regional model is doing better. The forecast, well, is outperformance the global forecast. So we can see that most of the month we can get a blue or a negative change in the forecast accuracy, which means that we are doing better forecasts with the regional model than with the global models. So I just show you here how we can, with dynamical downscaling, we can improve the skill of some of the individual members. But here we need to think about what is our goal. Do we want to have all of the ensemble members that come from global forecasts, even if they have core resolution, or if we wanted to resolve all of the spatial dynamic, the regional spatial dynamics that in this case are related with the upwelling, and just having a reduced forecast of the system. Now we are going to pass to the century projection. And in here, our dynamical downscaling system look a little bit similar. So we start with 3 global air system model. In this case, we are going to downscale or to make high resolution projection using 3 global air system model that belongs to the CIMI-5 archive, and we are picking one high emission scenario. This case is the RCP 8.5, and we pick these 3 models. For now, I'm going just to call them Hadley, IPSL, and GFDL, just for you to be familiar with the names. And then we use the output of this model, and we use it to build the forcing of our century projection that we are going to do with our regional ocean model. And in this case, we are going to be coupling our physical model with a biogeochemical model, so we can resolve other variables that are more related with biogeochemistry and primary productivity. So our control run, so I'm showing this, maybe there is not so much detail in here to go, but I wanted to mention that we did a control hindcast that will be like, this is our historical run that we know that we want it to look like. So this has this forcing, some reanalysis. We use ERA 5 in the atmospheric forcing. For the heat fluxes, we use a mixture of these 2 reanalysis for the winds, and then for the open boundaries, we use this reanalysis that is called SODA in monthly resolution, and the WOROS at Atlas. So to build this downscaling century projection, what we did is we take a time variant delta downscaling method. I'm not going to be talking so much about that, but the good thing about this method is that we can capture the changes in the interannual variability. We can also resolve the transient period that will go to 2006 to 2100, and also we can correct the bias of the air system models with respect to the observation during the historical period, sorry. So I'm going to be showing you these 3 downscale projections, ROMS CFDL, ROMS IPSL, and ROMS Hadley. But before that, I wanted to show you the impact, again, of bias correcting the forcing prior to downscaling. So here we have the mean of the winter and summer of the sea surface temperature taken from the observation. And if we take one of those global models that I used to do the downscaling, and we compute the anomalies or the bias of the sea surface temperature of the model with respect to the observation, we see that the global model has a warm bias during summer, and then during winter it has a less warmer bias in this central and southern part of the California current system, and then a little bit of cold bias in the northern part of the system. If we take the global climate model and we use it to force the regional ocean model, what we get is this bias without doing any bias correction. We get a bias during summer that is really similar to the model that is our original model or where we start from. But if we look at the winter, we get a bias that has been amplified with respect to the original global climate model. So this is why it's important that we bias corrected the forcing, because if we bias correcting the forcing, we get a less bias when we compare with the observation. And just notice here that I have to change the scale of the color bar, so in that case you can see something. So we can get almost 0.5 bias with respect to the observation versus the 4 or 6 Celsius that you have in some places with the global climate model. And the other part that this method is good is not only good just to reduce the bias of the global climate models, but also is good if you wanted to have a good representation of other processes that happen in the system. In this case, I'm showing how good is the representation of the California undercurrent. So we have here the control run, and this is a run that has been done with the bias correcting method. So just to walk you a little bit, so we have on the y-axis, we have depth, and then we have in the x-axis, the latitude. So we are taking, imagine that we are averaging everything that goes from 0 to 500 meter isobath all the way from the bottom of from the southern part of the domain to the northern part of the domain. So in color shading, we have the meridional velocity, and then we have some contours line that I highlighted here that are the potential density. And I picked the 26.5 of a core of the California undercurrent. So we can see that if we started for spring, we have a weak California undercurrent, and summer and fall, we have an undercurrent that is becoming stronger and is more developing. And then during the winter, we have a weaker undercurrent, but also we have the signature of the Davison current. And the same if we use the bias correcting of the forcing. However, if we don't bias correct the forcing, this is what we get. We get a spring with almost no undercurrent, a weakening of the undercurrent during the summer and the fall. We can even get an intensification of the Davison current in the northern part of the domain. But also notice how the isopycnal layers, now in this case, if we consider just the core of the undercurrent, we see how it has been deepened. So instead of being around 200 meters, now it's almost 400 meters. And this is important because when we are going to do this climate projection, we wanted to know where are going to be the water that we are going to bring into the region. So if we have this situation, this is going to also be affecting other variables. For example, we have spiciness as a variable that can tell you how are the water masses in the region, and also the dissolved oxygen. So if we don't bias correct the forcing, we are bringing water that are way more spicier, that is going to be more warmer, more salty water from the southern part of the region, but we also are going to bring way more minty water from the northern part of the domain. And now some result. I'm going to be focusing now on showing you some temporal variability and some of these anomalies projection. And the good thing of doing the dynamical downscaling is that we can represent the coast, because with the global model, when they have 100-kilometer resolution, they cannot resolve the coast really well. So I'm going to be showing you variables that are going to be averaged from 100 kilometers to the coast, and they are going to be, this variable, are going to be anomalies with respect to the historical period. And also I apply a low pass filter of 10 years. So we have here the three projections, the ROMS-EFDL, ROMS-IPSL, ROMS-Hadley, and the variables or the projection are going to be looking like this. We have x-axis with the time, and then the y-axis is the latitude. So we have here sea surface temperature, and we can see that the three projection of the three high-resolution projection, they are showing the same signal of the sea surface temperature. However, there are some latitudinal differences, but the main difference between the three of them is the magnitude of this anomaly. So we see ROMS-EFDL that is projecting less warming in the future when we compare it with the ROMS-Hadley that is projecting most of the warming happening by the end of the century. We can look at other variable, for example, meridional wind stress, and this is like a proxy for upwelling. So in here, think that when we have more blue, it's like we have more intensification of the meridional wind stress, and we get more upwelling. So more blue, more upwelling. So the ROMS-EFDL, we see that there is an intensification of the meridional wind stress in the central and also some part of the northern part of the domain by the end of the century. We see ROMS-IPSL almost not change with the historical period, but we see that there is a strong decadal variability during these 20, 30 years by the end of the century. And then we have ROMS-Hadley, where we have this dipole of the anomalies of the projection. We see that has an intensification of the meridional wind stress in the north, but we have a weakening in the south. So we are going to have less upwelling in this latitude. Another variable that this time is nitrate at 150 meters. This is a proxy of what are the nutrients that they are going to be upwell to the region. So we see that ROMS GFDL and ROMS IPSL, both of them show an increasing of the nutrients by the end of the century. But ROMS GFDL, this increase is happening in all of the coastal domain, while ROMS IPSL, this increase is just limited to the Southern California bight. And then if we look at the ROM Hatley, now the signature of the nutrient in the future is going to be different. In this case, it's going to be a declining of the nitrate by the end of the century. Oxygen, this will be just a mirror of the nitrate, just changing the signs. I'm not going to go so much in deep. Oops. But the one that I wanted to mention about is this variable that is chlorophyll integrated from the surface to 50 meter, and this is just a proxy for primary productivity. So if we take ROMS GFDL, we see that there is an increase of primary productivity in the central and the northern part of the domain, and this is because we are having an intensification of upwelling in this region, but also we are upwelling water that are rich in nutrients. If we look to the ROMS Hatley, we see that, okay, we have this dipole structure, we have some weakening and some strength of the upwelling in the future, but we are upwelling water that are more depleted in nitrate. So they ended up declining the primary productivity by the end of the century. And then if we look at ROMS IPSL, there is an interplay between the meridional wind stress happening here, not changing so much. We are not changing so much the nutrient, but also we are getting more the stratification that I'm not showing here. So this ended up having a signature of declining of the primary productivity by the end of the century. So with this, just a summary from here, I just showed you that the global climate model should be bias corrected and also downscaled to remove the systematic error and also to improve the spatial resolution. If we better resolve the upwelling dynamics, we found that it leads us to regional differences in the future changes. And also we found some large intermodal differences in the coastal region, especially for the biogeochemical variables. And I want to show you some application of this projection. So this has been applied to different kind of application that goes from fish distribution and population projection, where we have done it projection of coastal pelagic species, high migratory species, groundfish. We have also been used to make agriculture production projection in the future for the Southern California bight. Has also been used to do some projection in the marine protected areas, also to study the uncertainty, making some ecological decision of high migratory species, and also to do some social ecological vulnerability assessment. But from all of this, I wanted to be focusing on the fish distribution and population projection of the sardines. So for that, just to remind you, so we have our dynamical downscaling system, and now we are going to be focusing on this part. So this projection of the sardines has been done with different kind of models, but I'm going to be focusing on the first one, when we have projection from the individual-based fish models. So here we have the ensemble mean of the projection of the biomass of the sardine. So here we have the historical period, mid-century, and this will be like the end of the century. So we can see that by the signature, we see that the sardine biomass distribution is shifting northward by the end of the century, but we have some decadal variability happening in the middle of the century. We can see this decadal variability better with a time series, and here I'm showing the 3 projection and also the ensemble mean, that will be the black line. So we have a period of, by the mid-century, we have a decrease in prey availability. That's why we have a declining of the biomass of the sardine. But then by the end of the century, because we have an increasing sea surface temperature anomalies, we have more increase in recruitment. So we ended up having more biomass in the future, but also move to the north. And also wanted you to see how is the uncertainty of this projection. So we have 2 of the models that are projecting a double increase with compared to the historical period, but we see, if we look at the ROMS IPSL, that I just wanted to remember that it was not the warmer projection that we saw, is projecting 7-time increase of the biomass with respect to the historical period. So if this is the situation of the biomass of the sardine, we can also run projection of the future catch, and we can see that this projection of the future catch is going to follow the biomass of the sardine, obviously. So we projected that it will be an increase of 50 to 70% in the northern part of the California current system, but we will have a decrease of the biomass of the future catch of the sardine in the southern and the central part of the California current system. And this result has been also done with different models, with the population dynamics and the species distribution model. And here we change the variable to show this, the latitudinal center gravity of the biomass of the sardine. And just notice that in the three of them, with the time, we see that there is a shifting of the, or a move of the biomass of the sardines to northern latitude. So as a summary of this part, the simulated sardine population biomass exhibit a progressive polar shift. And this is driven by the thermal habitat preference. And following this distribution of the sardine biomass, the catch is also projected to increase in the north and also decrease in the south and the central California current part. And now we are going to move to the last part of the forecast, that is the decadal prediction. And here, what we have here is a time series of subsurface oxygen in the whole California current system that have been taken by different authors. We can see in here that, yes, there are periods where there are trends of declining oxygen, but if we consider the full time series of the subsurface of the oxygen, and by the way, this is oxygen in the isopycnal 26.5 and a deep isopycnal, we can see that all of the variability of the oxygen show a strong decadal variability. The problem is, and I think you guys know this more than me because I'm a model and I don't take observation, it's like having observation of oxygen everywhere is really hard and really time consuming. So because we don't have observation of oxygen everywhere, I have to come out with an index. And my index, if it wanted to show up, is based on subsurface salinity on the same isopycnal, the 26.5 in the California current system. Well, really this is the leading principal component of the subsurface salinity in the California current system, just to be more precise. But with this index of subsurface salinity, we can capture the decadal variability that we see in the observation of the oxygen. So now, what I wanted to know is like, okay, I have this index. I wanted to see how it relates with the rest of the large-scale signature of the subsurface salinity in the rest of the northeastern or Pacific domain. So here I'm showing the correlation of this index with the rest of the subsurface salinity anomalies on that isopycnal, the 26.5, at GR0. So we can see that, and the contour lines just represent the mean circulation in the subsurface. So we see that we get high correlation, of course, of the place where we have defining the index, and also we get some correlation if we continue the gyre circulation. So my question was, where did these anomalies come from? So to see that, I'm going to show you some correlation map that goes backward in time, if you wanted to show. So here we have the correlation map of 3 years lead time, 6-year lead time, and 9 years. So we see from the anomalies that we started here in the California current system, we can see how these anomalies are moving and they are following the gyre circulation. So we can see that these anomalies come from upstream the gyre. And if you know a little bit of the circulation, this will be related with the North Pacific current bifurcation region, more or less. Anyway, so we have this situation with the correlation and the propagation of this anomaly. So then my question is, okay, if we can find high correlation in this region here, can I use these anomalies 9 years before to try to predict what is going to happen 9 years later in the California current system? So I built an index using subsurface salinity anomalies in this region, and I did my forecast using those anomalies. And this is the forecast of this anomaly, trying to predict what is going to happen in the California current system 9 years later. This was part of my PhD thesis, and by that time, you can see that we didn't have observation, but now we have a good observation. At least we have many ergo flow that I can validate the forecast that I did some years ago. So now if I use the ergo flow that has been around for that period of almost 10 years, I can show the validation of my forecast that I did 7 years ago. So this gives us forecast potential using this advection of the anomalies around 8 to 10 years. So it's a different way of doing prediction instead of using just a model. So to show you that the strong decadal variability that we found in the subsurface dynamics can be exploited to do decadal prediction of tracers, in this case, for the California current system, with a forecast potential of, between 9 and 10 years. And with that, this is the end of my talk, but I wanted to summarize with some of the key points. And one of them is that bias correcting the global climate forcing prior to downscaling is key if we wanted to produce a skillful seasonal forecast and also climate projection for the regional dynamics. We need to find a balance between if we wanted to resolve all of the regional spatial dynamics and define scale circulation of the processes versus if we wanted to use all of the available ensemble of the global models that you can capture more uncertainty with that. And then finally, we can use the Bayesian scale propagation of the anomaly to try to exploit them to make decadal prediction of the California current upwelling system. With that, I wanted to thank all of my co-authors. I'm happy to take any questions.
So people on Zoom can hear. If there are any questions, I'll pass around. So if you have any questions from the audience.
Do you think that there's a way to incorporate the last part about decadal variation into predictive, like, downscale models, so you are able to capture the variability with either decadal processes or the ENSO cycle?
Yeah, the problem is a little bit more complicated because you will have to have a regional model that is large enough so you can capture, for example, all of the propagation, like all of this part. See, having a model that is occupied all of this region is tricky. I mean, there are already models that will cover all of this, but it's possible. It's just like the mechanism of doing the projection, the forecast is going to be different because you cannot have, I don't know if you will have so many realization of this just process, versus having all of the other one where you take, okay, this is my sea surface temperature and this is the projection of all of the time. Here you have to capture a process. So you have to be sure that first your model can reproduce that because this is based on observation, well, on reanalysis. It's like observation of, if we wanted to call them observation or reanalysis. But yeah, it's possible.
Thank you.
I have a question.
Yep.
That when you showed all in the first part the variables that were doing well and the variables that were doing poorly, it looked like wind stress was doing poorly, but I would have thought that you would need accurate wind stress for all the good variables to work out. So why do you think wind stress was poor, but you could still get some of the other variables doing well?
Well, there are many reasons why we got that. So one thing is we were comparing with the forcing of the model. That was our truth. That's one part. But I think we can get more of the circulation because the wind stress at the end is going to be based on what is your atmospheric forcing. More than you cannot do anything with your ocean model to try to capture that. Well, you can get some of the fluxes back between the heat fluxes and the wind stress to get it better. But I think the circulation part in the ocean is the part that we get better with the regional ocean model than the atmospheric component. If that answers your question.
I kind of have a follow-up question to that. So when you were looking at the variables that did well and did poorly, one of them that did well was buoyancy frequency. But I noticed it didn't do well with a shorter lead time, but it did seem to do better as the lead time went on to 4, 5, 6, 7, 8 months.
Yeah, I think with that one, it could be also related with the, I forgot the name of this. When you have in winter time and then you pass to summer times, because those are the one, I had to check that with the July forecast to see if what I'm telling you is true. but it could be related with the reemergence of the anomalies that happen during the winter and summer. So then you start getting again more of the anomalies or getting better forecasts of those anomalies during summer.
Okay.
Yeah.
Awesome. Thank you.
I have one more question.
Yeah.
You showed the sardine forecasting. Did you do anchovies as well? And if
I
so,
didn't do that part.
I'd
Just to
be
be clear, I
interested to see
didn't
if
do
there
that.
were any, if there was a decoupling of those.
I don't know. That's a question for Jerome. I haven't done
Okay.
that part. It's just I thought it would be cool to show some ecosystem variable that maybe you are more familiar with. That.
We'll stay tuned.
Yeah, I'm pretty sure that maybe he did. I'm not so sure. Yeah.
Oh,
For your decadal prediction
Yep.
forecast, you mentioned that you used Argo floats for the validation. I was wondering if you also used that when doing forecast for hindcast validations, or if there were other in situ instruments that you used for that as well.
So in the paper, I think it compares with other observation, but the main one that I show here was with a reanalysis. So we were taking the reanalysis are or truth. But you can do those forecasts because that is the part when you get the truth. I mean, the real skill is when you compare with observation. And actually, that is the other part that is related with the part of doing the decadal observation, the decadal prediction. It's hard because we don't have so many observations that you can really say, you can tell, or you can say that there is prediction or forecast skill, but until you cannot compare with the observation, it's like, yeah, this is theory, basically. And we were using, just if you wanted to know, we were using the reanalysis that is done for the California current system by the UC Santa Cruz. I don't know if you're familiar with that, but there is a reanalysis that it takes data simulation. So that is what we were considering the truth of the thing that I showed you right now.
So you showed 3 types of bias correcting methods, I guess, when you're trying to bias correct the downscaling of the global data. Is it recommended to use multiple bias correcting, or can you pick and choose, or is it the more you use, then the more accurate your predictions will be?
It's actually depend of what is your goal. Like in our case, for the projection, we wanted to correct the mean bias. So we use a method that was called that. But if you wanted to correct, for example, the variance instead of just the mean, if you wanted to correct the variance, you will have to use another method. I don't know if people usually take 2 methods together because that will make complicated at the end of the day, not because of the math, but I'm thinking if you correct your mean and your variance, how the 2 of them are going to change, you know? But my main point is like we really need to do the bias correcting because it's not the same having projection where the fish is going to be a change of, well, the changes doesn't really matter because the change is going to be the same, the anomaly. But the important part is going to be your fish is not going to be affected by the same, if it's going to be 15 degrees or if it's going to be 25 degrees. I have the feeling that the fish probably will not be that happy, and I'm totally making it up, those ranges of temperature, because I have no idea about fish. But that was the main idea. We did that to correct the mean bias because of the fisheries application.
Yeah, thank you.
Good. Can I see them too?
So, the first is from Basil, who is asking, said, thank you for the talk. Is there any effect of El Nino years on the decadal prediction?
In that one, not really, because I compare I try to see if the index of the salinity will have any internal or interannual variability like El Nino, PDO, or MPGO, and it was not affected by that. If not, I would have used any of those to try to make it. It would have a direct answer, but that one was not there.
And then Scott Hamilton asked, does the model track pH changes in the California current? And if so, how is the skill at making those forecasts?
So for the seasonal forecast, they don't have biogeochemistry. There was only physical variable. for the climate projection, they have pH, but that part was done by a student, by Jerome's student. I think her name, I forgot her name right now. Julia Cheres, and she's working on a paper about that, about showing the projection of the pH. So I'm going to leave you with the uncertainty of that until you wait for the paper. But yeah, the one more thing that I mentioned about that she didn't use this one that are 10 kilometer. She used projection from 3 kilometer resolution. And this is related with your question because to see the scale, well, we cannot see the scale of the prediction because that hasn't happened in the future. I guess we have to be 2100 to know if the prediction are good. But the reason why I mentioned this is because the 3 kilometer resolution model has better resolved the pH during the historical period. So the work that she is doing is working with a model that really well reproduces the pH during the historical period. And I can pass a reference about that if you told Mrs. Scott, no? Okay. Yeah.
Okay, I don't see any more questions, so let's give Mayor another hand. Oh, we have one more. Didn't see your hand, sorry.
I was really impressed by how how well the projections matched up with the observed at the very beginning of the talk for sea surface temperature. And I was just wondering, is the model so good that it was able to essentially predict any really abnormal events, such as like the big blob heat wave, or were you able to see any sort of variations where you were like, oh, that was something that happened that was very different than normal?
You mean to see that with the hindcast or to see that with the projection?
With the hindcast, when you're comparing what we've seen in the past to what the model is projecting, I guess.
Okay. With the hindcast, I haven't looked at that, but the signal will be there. It's just I haven't looked at the signal of the blob or anything, or any El Nino or anything. But for the projection, because it's different, because when you do the hindcast, you're taking forcing that is real, that is having atmospheric forcing and ocean boundary condition that real in the sense that they have the signature of El Nino, has the signature of the blob, has the PDO, interannual variability and all of that. But when you do the projection, we had to do the projection also starting from the hindcast, from the historical period. So our projection go from 9080 to 2100. In those projections during the historical period, those events, they are not there. But just because that is how the global climate model works, that they are differently initialized, their couple dynamics is not going to match El Nino year with El Nino years. But it can be done. You can look at for that. It's just that it's not going to be straight ahead as a, I don't know, 2010 was El Nino year. In my projection, it will be an El Nino year. No, you have to look for El Nino year in different years. So you will have to look for the pattern in different part of the time. I don't know if that answered your question.
Yeah, I think so. Thank you.
Okay.
That's it for the questions. So why don't we give Mayor another hand? Thank you very much.
Thank you.
She'll stick around if there are any lingering questions that you want to